Hello, we're back again. I don't know what's going on with Jade. We've given her the link multiple times. She seems to have authorization issues. I'm going to do it with Rumpus. If Jade gets her computer working and gets on the live feed, I will watch it this time. Sorry, guys. I saw all these people typing on the last one, the Rumpus and Jade, and Ozzy was in there. I mean, I'm sorry, guys. So I will watch it more prevalently, or persistently this one. Oh shit! Hang on. Okay, sorry about that. So you can tell I have the video open over there, so at least I do have the live feed going. Anyways, what this video is going to be about is going to be about the Monty Hall problem, which I think most people really know about by this time. There are a few people I still get messages from that try and convince me that there's really there's no advantageous benefit to swapping on the Monty Hall problem. So what I'm going to do is I'm going to give just a real basic overview of it. I'm going to let Rumpus get into some details on it, then I'm going to do an enumeration on it to show that if you pick up a specific door, what happens to the probabilities and why mathematically you will always have an advantage to swap doors, and specifically a 1/3 increased mathematical probability. So you basically go from having a 1/3 initial to 2/3 by actually swapping. So I'm going to screen share real quickly here. We don't have much time. These are going to be a quick video. It's probably going to be about 20 minutes at most. Maybe, we'll see. So this is the way the Monty Hall problem goes down. Monty Hall was a host for a show called Let's Make a Deal. And basically the way he ran this was that he presents you 3 doors, and behind 2 doors is a booby prize. We'll call that a goat. Okay, we'll call that G. Okay, so G is equal to a goat. And then there's a good prize, and we're going to call that C. We're going to call that a car. We all like cars as prizes until you realize you can't pay the sales tax on it. Anyways, so he has certain conditions, and the conditions of this problem are such that Monty Hall always has to offer you the opportunity to swap. So you pick a door, he'll open a door that's not your door and not the car, and he will always offer you the opportunity to swap. So the way it runs is this. You have the 3 doors, and he says, pick a door. So I pick door 1. He'll then open door 2 or open door 3. Let's say he opens door 2, and then he says, okay, 2 is a booby prize. It's a goat. Now he asks you, do you want to keep the same door you've got, or do you want to swap to door 3? We will show you, the Rumpus and I will show you that it's always better to swap in that particular case to door 3 and increase your odds. So this is the way it looks initially. I'm going to turn over to Rumpus right here. Rumpus, go ahead and give some more details on the Monty Hall problem. In your slow, methodical voice that you have.
Right, I must admit, I haven't revised on this, so I might get caught out here. I can't remember what. Will you choose one, and then he? Do you want me to explain the ratios as far as it goes? Just what he does?
Yeah, go ahead. And I know I'm screen sharing, right?
Yeah, okay, I can see.
I'm gonna switch back between the other thing so I can look at the live chat because you might be in there. So. Anyways, go ahead. So the whiteboard. Go ahead.
You're not presenting. Yeah, so we've got 3 doors, and behind one door, I think there's nothing. Then there's a goat and a car. Is that right? I think those.
There's 2. There's going to be 2 G. Okay, 2 goats.
That's right. Yeah, there are 2 goats. That's right. Yeah,
there's going to be 1 car. Okay.
Right. So
this is your total probabilistic space.
Yeah. So distributed between those 3 doors are those 3 objects, and then I've got to pick 1, 2, or 3. And then Monty Hall will say, okay, I will. So if I pick 2, he will then open up either 1 or 3 and expose a goat in either of those doors, and he can pick either one. So the question is now, so if I've picked 2, and then he says, and opens up number 3 and then shows a goat. So the question is, he then says, what would you like to do now? Do you want to stick with your initial selection of 2, or do you want to now move and switch to number 1? And you might think, and most people do, that, well, I've picked 2. What's the difference? There's a 50-50 here. It's the goat's either in behind mine or the other goat or the car. So it's 50-50. There are just 2 options. It's 50-50, isn't it? 1 out of 2, that's 50-50. So most people think, well, it's 50-50, and people are always reluctant to change what they like to stick. Is a natural psychological tendency to stick with what you want to do. So people stick with it. So I would stick with number 2. Naturally, but unfortunately that's not right. In fact, because the chances are the best thing to do is to swap, and you get a 2/3 chance if you swap and only a 1/3 if you stay here. So it's twice as good to swap the not.
Correct. Yeah, that's exactly you described it perfectly. So let's run it through a scenario and do that. I'm going to erase this goat card because we know what these things stand for, and this whiteboard doesn't allow too much space on here. I just found this the other day, so I haven't really played with it. Excuse if it's not great handwriting. I'm using a mouse to do this, so whatever. Okay, so let's run a scenario. So let's say I pick door 1. Oops, let's get rid of it. So I pick door 1. Okay.
Well, do you want to be Monty Hall and I'll do the picking?
Well, actually,
or do you want to do it the other way?
Let's just run it this way. Let's actually know what's behind here. Let's say that we have the goat, and we have a car. Okay, you don't know this, but this is what's actually behind these doors. Nothing, no matter what you pick, you agree that none of these are going to change, right?
Yeah. Do you want to put a G or a C behind the various doors, and then we'll go through it?
Yeah. So I have there's a goat behind 1, goat behind 2, and go for.
Do you want to draw the G there?
I did. Did you see it?
No. Oh, no, there we are. Right.
Okay.
Sorry. Yeah. No.
Okay.
Now we can see it. Yeah.
Okay. So this is unbeknownst to us, but Monty knows. Okay. So I say I want to pick door 1. Okay. He's limited what he could pick here. Okay. Because if you notice, he cannot pick door 1 because you picked door 1, right? He cannot pick door 3 because 3 has the prize and then the game ends. He's not going to pick that. He can't pick that. He has to. Remember the rules and the conditions of the game. He has to always offer you a swap. If he was to open this door, he could not offer you a swap because the game's over. Correct?
Yeah,
okay.
Definitely.
All right, so he's limited here. He can only open this door. He can only open 2. Okay, so I'm going to do a little what's called an enumeration. I'm going to say run it with door 1, and he opens door 2. So I'm left. This door's taken out here. So I'm going to draw.
Yes, and we can see the goat. He opens the door, and we can actually see the goat behind the door.
Yes, you can open the door and see the goat. Now, initially, again, each door has a weighted probability of 1/3, 1/3, 1/3. We all agree with that. And you have 1/3 plus 1/3 plus 1/3 equals 1. That's your probabilistic space has to equal 1. All outcomes have to eventually equal 1. We know this for basic probability. So, in this case, something has to change here. So if I open door 1, if I pick door 1, he opens door 2. These are my options here. He has to open. This is the door. I'm going to say this. I'm going to do. I've never really enumerated this particular way, but I think it should be the same thing. So if I pick door 1, okay, the door he opens, I'm going to say open. Man, this is really hard to do this with mouse. Okay, it's 2. Okay, and the outcome. I'm just going to say OC for outcome. Okay, because I'm running out of space here. Is a win. Okay, and I'll show you why in a second. So. Remember we said initially that every time you swap, you have a better chance of winning. So what happens if you swap in this scenario? I pick 1 Rumpus, and I say I want to swap. Do I win?
Yes.
Yes. So I pick 1. Going by my thing here that I swap, I win. So I actually increased this 1/3 here actually was given to me. So I by picking door 1, I actually have a 2/3 chance. Oops, chance to win. Okay, rather than
just because it looks like 50-50, the odds have not changed since they started.
Right. Yeah. Nothing's. I mean, my initial conditions were 1/3 to win. That cannot change. My initial conditions are never going to change. I always have a 1/3 chance to win. But it's like winning the lottery. The lottery is a binary outcome of win-loss, but you don't have a 50-50 chance of winning the lottery. There's a different probability of you winning to losing. You have a much lower probability of winning than you do losing. So you just because you have 2 outcomes does not make it a binary outcome. So let's go to the next one. And I'm sorry this is so sloppy here. What can I do? It's a whiteboard. So I'm going to pick door 2 in this next scenario. So I shouldn't have drawn. So I pick door 2, and we get this door back in play. I'm going to erase this little line.
My screen isn't changing. Oh, there we go. All right.
And we have enough technical difficulties here. Jade's having a problem with her router. That's what I think it is. But unfortunately, we are limited in time, so I had to begin this, or I won't be able to do this today. So, okay. So back to our initial thing. Now, if I pick door 2, okay, obviously Monty Hall cannot pick door 2, right, Rumpus? Because you picked.
Yep.
Okay.
That's right.
And what's the other door he can't pick?
He can't pick the one with the car in it, of course.
He can't pick the one with the car, so he's limited to pick door 1. Now, so in this enumeration, I pick door 2. He opens up door 1. I swap. Do I win?
You do.
I do win. So big win there. All right. So far, in 2 cases that I've swapped, I win. Hey, looking good. Now, let's look at the third scenario. The third one is where people get a little bit confused here. Let me check if Jade's messaged me yet real quick, just in case. Nope, not yet. Oh, right here. She's switching computers. But anyways, I have time. I'll do another video. It's only 2. I probably can use the computer till 3:30. So, all right. So I picked door 3. Now, Rumpus, do you want to try this, or do you want
well,
just?
Well, presumably he can now pick 1 or 2 to open.
1 or 2, yes.
Yeah. So let's suppose he picks 1.
All right.
That shows you the goat behind door number 1.
Okay, let's say he opens door 1. Here's the big thing before I continue. He can open 1 or 2. It does not matter which one he picks. Okay, he can pick either one. It makes no difference to the outcome, and I'll show you why. So you say he opens door 1, right? Yeah. Okay, I swap, and I have to swap to door 2.
Yeah.
Okay, so he opens 1 or 2, and I swap. Do I win or lose?
You lose.
I lose. Big time lose. So
because you opened up door number 2, because you initially selected 3, and you picked 2 because you had to swap, because that's the rule we're putting in, and therefore you get the goat in door 2.
Yes. So if he would have said, instead of opening 1, he would have opened 2. You're saying that it doesn't matter, because if I'll choose. If I swap to 1, I still lose, right?
Yeah, that's right. Yeah. Because our procedure we're suggesting is to always swap as a best procedure, isn't it?
Yes.
So
yes. Because swapping is the best way to go. So we decided these are three possible things depending on what door you get. Okay, you pick. So you pick door 1, he opens door 2, you win. If you had picked door 2, he opens door 1, you win. If you pick 3, you're fucked anyways. Okay, I mean, you're done. So you're never going to win if you swap with door 3, because you've got the door with the correct winning door. You got the one with the card. So obviously, if you swap, you're going to lose. It doesn't matter if he has 1 or 2. Okay, so this is the amount. This is called the enumeration. This is basically 2 times in this scenario you win by swapping every time. And there's only 1 time you lose, and that's a 1/3. So basically, out of these, you have 3 different things. And what do we have? We have 2 out of 3. You win by swapping. Oops. And you have 1/3 lose by swapping. Well, this is not as easy as it looks, guys.
Yeah.
Anyways, but you can see it, right?
And of course, if you hadn't swapped, it'd be round the other way.
Yeah, actually, if you don't swap, if you don't swap every time, you only have a 1/3 chance to win.
Yeah. So you have twice as much chance of winning if you swap than if you didn't.
Yeah, because let's run that real quick. That's a good thing. Let's say we don't swap. So we pick door 1, we don't swap. Do we win?
On this particular scenario, no, we don't. No.
Yeah. Well, so we pick door 2, we don't swap. Do we win?
No.
Pick door 3, we don't swap. We win. But unfortunately, there's 2 goats in 1 car, so there's 2 chances, 2/3 that you're going to lose, not by swapping, and only a 1/3 chance you're going to win. Or excuse me, if you don't swap, and only a 1/3 chance to win if you don't swap in that particular scenario. So
yeah, that's quite good actually to actually just demonstrate that just by ignoring the door swapping, just the fact that if you pick each one, you can see that you're only going to get 1/3 because obviously it's just selecting one of the 3 doors. You're going to get a 1/3 chance if you don't change.
Yes. And I'm watching the live feed for Jade because she has a computer, and the Schiff actually just points out. He says what confuses people is that no longer random chance. It's no longer random once the host chooses which door to remove, and actually it's no longer even random. Period, in a way, because these things are set. The GGs are set. Once you pick a door, you're deterministic at that point unless you swap. Once you pick a door, you're deterministically going down the path. Randomness is over. You have a 1/3 chance. The only way you can change that is by swapping to give you that additional 1/3 chance to give you 2/3. So when he opens the door, I think this is what Deshuf is going to say. When he opens that door, people think the event starts over again. They think it's a new event. They don't realize that if you start with the 1/3 chance, of the correct door, I guess it would be this one. The 1/3 chance to win the correct door, that does not change during the event. It's not like flipping a coin, and I'll explain that in a second. It's not like deal or no deal. In this particular situation, you start with 1/3. You've got to end with 1/3 if you don't take any actions.
Yeah, that's the key. That's the key
That's
thing.
the key. And of course, we all know with the coin toss, though, what happens if I flip a coin 4 times in a row? What's the odds? And it comes up heads every time. What's the odds of it doing the 5th time heads? Well, it's 50-50. You know, because each one is an individual event. Here, it's not the same thing. You know.
Sorry, the other useful thing is, of course, to consider. Let's suppose there were 99 other doors. Besides, you had 100 doors in total, and then you consider the odds. That also makes it very clear to some people.
That's a good one. Let me do that one. That's that is very true, and I've used that before. So let's do that. I'm not gonna draw a bunch of doors, but let's say I've got door, door, door. I'm just making them circles at this point because it's easier to do now. So
yeah, just.
So I've got all these freaking doors. I got all those, you know, down, down, down. I got you know, let's say 100 of these doors. Okay. This is not as easy as like. I hope nobody ever watches this video. This is embarrassing. Anyway, so I got 100 doors. Let me check invade real fast because I really hate that we've done this.
Can you just draw? I mean, you could just think of it. If you had a Word document, you could just draw 100 full stops or something.
Yeah, I guess so. But anyway, this works. So I got a bunch of doors here. Anyways, we're going to say this first door here. What is the odds if I pick a door at random? What is the odds of this door being the winner? It's 1 out of obviously 100, right? And
if you stick with it, of course, that's what it's going to remain.
Right. So if this is the car, okay, let's say all these other ones are goats. Okay, well, you know, blah, 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 these are goats. This is the worst diagram I've ever done in my history of my entire life. Oh, my God, this is embarrassing. But anyways, you get the gist, man. But so this is my car, and the car is at 1 in 100. So basically, if you pick this, you got lucky if you don't swap. But let's say if you do swap. Let's say you pick this, and he picks one of these other doors. Remember the scenario with the third door that if you picked 1 or 0, that it doesn't matter, right? We said it doesn't matter if he picks 1 or 0. You lose either way. So if you have the winner and you swap, you're going to lose every time. It doesn't matter. So let's say he opens this door here. He opens door 2, and he says. Actually, you know what he's going to do is because of the 100 doors, he's going to open all these other doors.
But he's going to all the 98 other doors.
Correct.
Leaving 1.
So all these other doors over here, let's say he opens all these other 98 doors. These are gone. And he leaves 1 door left. Okay? That door is going to be a goat, obviously. If you swap, you lose. However, what the reverse situation is, if you started with a goat, okay, and there's a 99 over 100%, that's not percent, but a fraction, 9 over 100 that you're going to get a goat. He opens all these other doors, but what's left? The one with the car. Oh. So if you pick any, you pick one of the doors, you have a 99% chance that you're going to pick a door with a goat. Since he's opening all these other doors, just leaving the car, you have a 99% chance to win if you swap. Right? Boom.
Yep.
So any one of these things you swap, you win. 99 doors of that. The only time you could lose by swapping is if you initially picked the door with the car to begin with.
The car,
so, yeah. There's stuff presenting. So, anyways, that's the Monty Hall Problem in a nutshell. Again, not too difficult, not too technical. I like to keep things simple. I'm sorry that Jade couldn't join us because she's having router problems. Rumpus, anything you want to add to it? I mean,
no, I think I covered it pretty comprehensively, I think, actually.
I do have people actually sending me email already, actually. On my last video, I asked, what do you want maybe to go over? A couple of them are a little bit more in-depth than I could do right this second. They're not out of the possibility, however. Jade actually wants to do one with radiocarbon dating, and she wants to explain it using differential equations. She's going to send me that stuff, and between Rumpus and myself and her, maybe we can work our way through that. They're not that hard differential equations. I mean, I was showing like Rumpus like where I'm at. I'm like, I can do a simple separatable linear homogeneous, the first order, basic differential equations. One of those. We basically all remember how to do that kind of stuff. But some of the other ones using integrals of substitution, I haven't done it in a very long time. But the actual understanding of the radiometrics and the the decay rates and how that kind of goes into P equals all T, or P equals E or T, and half-lives. I can remember that a little bit. So
that's just a simple exponential decay, isn't it? It's barely a differential equation, is it?
No,
it's only just about.
No, that's an exponential function. But what's funny is I had it brought up the other day because how Hovind loves to bring up that the initial candle. You don't know. You can walk into a room and you see a candle, but you don't know, when the candle began. You don't know when it was initially lit.
Yeah, yeah.
I'm still. You're gonna have to explain to me what the hell he even means by that.
No, I
It's
don't
so far out
understand.
of my ability to dumb myself down to even understand how there's even
It's
a
not
rational
possible.
thing.
It's not. It's irrational. Therefore, you can't rationalize it.
Yeah, it makes no freaking sense. It's a completely gross misunderstanding. And I even had our favorite buddy Arcane, our structural engineer genius. I got asked him, I said, if you have, if you have something simple like P equals E or P equals E or T. So I have the initial primary thing of something. I have my the final equals initial plus Euler's number raised to RT. And I said, Arcane, if you know, our Euler's number is a constant, okay? If you know R and T, and you know your initial, you can rearrange the formula for the final, which is actually what it starts out with. But if you say you know your final, you can find your initial. Or if you know R and you know final and initial, you can arrange it for T. Or if you know T and final and initial, you can rearrange the formula for R because E's a constant. This is basic algebra, right? Sometimes it's not that easy to do. When you have an exponential, I realize it is a little bit difficult for some people to manipulate those using natural logarithms. But
Yeah.
for the most part, it's not that hard. You could do it.
Yeah.
It's not that hard. Rumpus could do it.
Yeah, we can. But I think for people who haven't done, I think you might be slightly overestimating the intellectual knowledge of the people you're thinking about, just because you've done it before.
Well, but the whole principle was if you got 4 variables and a constant, and variables, you can rearrange it to find the last one.
But when you shove an exponential in there with an e in there, they get all they're going to get all upset. That's going to be, you're talking about what, top 5% of the population probably, or something, I suspect.
Oh my goodness, I couldn't get it across to him that again, you can find a variable if I've got x equals yz, and I know yz, I can find x.
When you say yz, you mean y to the power of z?
No, I'm not even using exponential. Let me draw this out. If I have y to the, let me know my whiteboard. I'll have to end this soon because it's getting off topic, but for those who are interested, it's not that complicated. But if I got x equals yz, if I know these two, I know x, right? For the same token, I can rearrange the formula. I can divide each side by y, right?
You're not presenting, by the way.
Oh. See, this is why I'm glad I got somebody in here to keep me honest here. Is that better?
Ah, yes, there we go.
All right, so if I know y and z, I can find x. Now, if I want to rearrange the formula to find z, all I do is divide each side by y, right? So I'm left with x.
I really think you should be using Word here or something similar. This.
It's hard to see.
No, it just means if you just use Word, you could do things over things, whereas trying to draw it, I think, is just...
Well, I use LaTeX, actually. Yeah, no, I use LaTeX usually.
Yeah. Oh, do you? Oh, right.
Yeah, I use LaTeX program, so it's a lot easier. Maybe this is easier to see. So x is equal to, okay, and I use this little symbol here for z. So basically, if I divide each side by y, Arcane logos, this is something you learn in 2nd grade mathematics. I'm dividing each side by y, these cancel out, right? So I'm just left with x over y equals z. And then I just rearranged it and did it backwards. So z equals x equals y. But I mean, it's okay. If you know 2 out of 3 things, you can find the last one. That's all I was trying to explain to him. So he just didn't seem to grasp it for whatever reason. But anyways, I'm sorry, Jade, that once again that you didn't be able to join us. I know you're having computer modem issues. She said she was going to try to get on the computer. She wasn't able to. Maybe for the next one. I don't know if I have time for something else, but I'm getting emails right now. We'll see. But Rumpus, thank you, my friend, for joining me. I think we went over it pretty quickly. I think we went over efficiently. I think we just made our case, right?
We did.
We did. Thank you, good sir. And why again is it better to swap?
Because you double the chance of you winning.
Yes, and because math works, bitches.
Right. So, yeah.